Here. As already said, the topic of my talk is a singular value decomposition in spherical surface wave tomography. This talk will be rather analytic. So at first I give a small motivation from spherical surface tomography. Then I define the arc transform, which I will work on, and in the last section I will concentrate on some special cases. Okay. I start with a very classical problem, the so-called Funk-Radon transform. We are on the two-dimensional sphere S2, which is the set of unit vectors in R3, this yellow thing. And we consider a function from the sphere to the complex numbers. And now the Funk-Radon transform, which is also known as Funk transform or Spherical Radon transform, maps a function to all its integrals along all great circles. And we parameterize a great circle by the vector perpendicular to it. So here it's xi, the north pole, and the circle perpendicular to it is the equator in this case. And we do this for all vectors xi. And the resulting function is the Funk-Radon transform. And it is well known that every even function on the sphere can be reconstructed knowing its Funk-Radon transform. Why only even functions? Well, when you look at some great circle, you will see that a great circle always contains a point and its antipodal point. So we cannot distinguish between these points when we just know the integrals along great circles. So on odd functions, this Funk-Radon transform obviously vanishes. So we can get injectivity only for even functions. And I will consider some generalization of this Funk-Radon transform motivated by a spherical surface tomography. So what do we do? So spherical surface waves, they propagate along the surface of the Earth. And the speed of propagation depends on the position on the Earth, basically maybe because there are different materials on the surface, so the speed of propagation is not constant. And we measure the travel times of these surface waves between many pairs of epicenter and detector. And from all these measurements, one wants to reconstruct this local speed of propagation or speed of sound. A very common assumption we also do here is that we assume that these surface waves propagate along the arcs of great circles. So you could at first assume that such a surface, that with this local speed of propagation, you get some metric on the sphere, and these waves don't propagate along these great circles, but this propagation goes somewhere near a great circle. But it is common to assume that they propagate along great circles, and this travel time is just the integral over this speed of propagation. Some references, at first the paper of Paul Funk from about 100 years ago, who introduced the Funk-Radon transform. Then this paper from Woodhouse and Zajanowski from the 80s, which were the first to do this spherical surface wave tomography. Then some more mathematical paper on this surface wave tomography. And finally, the thing I will talk about today. So now we define the mathematical operator, this arc transform. We have again a function from the sphere to the real numbers. In the case of surface wave tomography, this function is 1 over the speed of sound. And for any pair of 2 points that are not antipodal, there is a unique shortest great circle arc connecting them. And at first we define this transform just as the integral of f at this great circle arc between these 2 points. However, this definition has some problems. So here we have basically from a function on the sphere to sphere times sphere. But the problem is when these points become antipodal, then you can imagine, like between the North Pole and the South Pole, the great circle arc can be any meridian from the North Pole to the South Pole. So this, even if the function f is continuous, this transform defined in this way is not continuous because of this problem with antipodal points or with points that are almost antipodal. So we decided to use a different parameterization just to make this continuous, so it is mathematically better to describe. What do? We instead of the 2 points, we have one parameter psi as the length of this arc, which is the arcus cosine of the scalar product of these 2 vectors. And then we define a rotation q on the rotation group SO3 such that this vector xi is mapped onto the equator and this other vector eta also on the equator, and they have latitude minus psi over 2 and psi over 2. And now we define this operator from continuous function on the sphere to, this time it's really a continuous function on the rotation group times the interval. So the rotation group is the rotation to the equator, and this is the length. And we define it as this integral between these 2 points. Yeah, I promised a singular value decomposition. Before we come to that, we need some notation. At first, on the sphere, we introduce spherical coordinates with the latitude phi and the longitude theta. And an orthonormal basis on the sphere is given by these spherical harmonics of degree n, defined like this. So basically, the associated Legendre polynomial of the polar distance times this exponential function. These are polynomials of degree n on the sphere, and they form an orthonormal basis of L2 on the sphere. Now, on the rotation group, just as a reminder, the rotation group is the set of all 3×3 matrices that are orthogonal. Basically, the inverse is the transpose of the matrix, and their determinant is equal to 1. On the rotation group, we can also define some orthogonal bases times, because these are just not orthonormal. These are not normalized. These are the so-called rotational harmonics or Wigner-D functions. This is a very simple definition of them, basically just the as coupling coefficients between some spherical harmonics y and k and y and j, where we rotate one of these spherical harmonics with the matrix Q. And these functions d and k also form an orthogonal basis on the rotation group. And now we come almost to our singular value decomposition. This is already well known. So this A was the arc transform of applied to some spherical harmonic. And it is known that this can be written as a sum over, at first, these p and j tilde of 0, which are just coefficients given by this formula containing some double factorials. Then d and jk, the rotational harmonics in the Q, so on the rotation group. And with respect to psi, so the length of these arcs, we have this function Sj, which is basically sinus j psi over j. except if j equals 0, then it's just psi. So this was well known, and it turns out that this is also a singular value decomposition. So here we go. Basically the same as on the last slide. So the arc transform A has the singular value decomposition. The functions on the sphere are these spherical harmonics, and the functions on the rotation group times the interval are these E and K, which you've seen on the previous slide. Here below, these are just the normalized versions of it, and the singular values given by this formula. And we also shown that these singular values decrease like 1 over the square root of n, which is kind of expected because we integrate along one-dimensional manifolds. So these singular values drop like 1 over the square root of n. What we can still see here, this operator maps from a function on the sphere to rotation group times the interval, so from a 2-dimensional to a 4-dimensional manifold. So the inversion is still very overdetermined. So it makes sense to look at some special cases, to just look at certain arcs, and we ask ourselves, is this transform then still injective? So we start with a very simple case, just with the first parameterization. This time we look at all arcs starting at the north pole, so we fix one endpoint of the arc, and the other endpoint is just anywhere in the sphere. This is the definition, so just the integral between the north pole E3 and any point on the sphere. And it is easy to see that such a function, that any function f can be recovered from these integrals just by differentiating along this theta. Okay. Some generalization of this theorem was found about 10 years ago from M.A. Bikian. He considered S as an open subset of the sphere, and this S is basically the union of two sets A and B. And now we consider the arcs from any point in A to any point in B. And we say that the integrals along all these arcs are 0. Then the theorem says that f must vanish on the union of A and B. This contains the previous case, just if we say that A is one single point. But it's still that we have like full data on A and B. So another thing we could look at this time, we have a convex set omega on the sphere. So convex just means that the great circle arc between any 2 points in that set omega are still in omega. And we also want that this set is strictly contained in one hemisphere. Then we assume that the integrals of f along all circle arcs between boundary points of omega vanish. Then we get that f vanishes on omega. So in contrast to the previous case, where we had basically the integrals between all points, now we just have the arcs between boundary points. And the proof of this theorem is surprisingly simple. At first, we extend our function f outside the set omega, basically because we are only interested in f inside omega, so we can do whatever we want outside omega. And now I claim that if this condition is fulfilled, then the Funk-Radon transform vanishes. Why is that? Well, just take any great circle. What could happen? Of course, it can be that the intersection with omega is empty. So then this great circle is just outside omega, and the integral is 0 because f is 0 there. And if it intersects omega, then the intersection of this great circle with the set omega is such an arc between two boundary points of omega. And we assume that this integral between the boundary points is 0, and the integral on the rest of the sphere is also 0 because f vanishes there. And by our injectivity theorem from the first slide, we know that the function f must be odd when the Funk-Radon transform vanishes. So, and we also know that this f is supported inside the hemisphere because f can only be supported in omega, which is contained in the hemisphere, and an odd function that is supported inside a hemisphere must vanish. So we've proven that. And now we come to the last generalization I want to, the last special case. This time we fix the arc length, and then we name this operator a psi, depending on the arc length, and this maps from the sphere to the rotation group. Here are some examples of circle arcs with fixed arc length. And it turns out we also get a singular value decomposition for this case. Well, the formula looks quite similar to the previous one. The singular functions on the sphere are again the spherical harmonics. And on the rotation group are these functions z, which are defined here, look basically as they did for the singular value decomposition in the full data case. And the singular values have this explicit formula. And the singular values don't vanish, so we also see that this operator a psi is injective. And now we take a closer look at the growth of, or better say the decline of these singular values. So we know that these singular values should decline like 1 over the square root of n. So that's why I've plotted here the squared singular values times n. And this should be bounded. So we start here with a small value of psi, so very short circle arcs. And we have here the singular values depending on the polynomial degree, so on the degree of the spherical harmonics. If the length grows, the singular values also grow until we come to psi is pi. So for pi, we have circles with arc length pi, so half circles. And now they look, they are basically constant here. But then when the circles become a little longer, they look like this. So they are different for even and odd degrees. If we think about it, why is that? Well, you know that spherical harmonics of odd degree are also odd functions. And when you integrate an odd function on a circle that is bigger than a half circle, we have some cancellation again between these antipodal points. And now when psi gets even bigger, so the circle arcs approach full circles. Here for 2 pi we get full circles, which is the Funk-Radon transform. Then the odd singular values vanish because of this cancellation. these are still the singular values, but plotted the other way around. So here we have psi in the x direction, and we let n vary. Here on the left side we have even n and odd, and on the right-hand side odd degree n. And if n grows, we see that these approach some limit, such a piecewise linear function. And we could also prove that this limit of these singular values times m, that this converges to such a piecewise linear function, which is different for even and odd degrees. Some particular cases, we've already seen the case of great circles. There we have the Funk-Radon transform, which is only injective for even functions. And then the half-circle transform was already shown to be injective about 20 years ago. And here there's also a recent paper which showed that this half-circle transform is even injective if we take just half circles in the northern hemisphere and half circles in the southern hemisphere. With that, I come to an end, and I would like to thank you for your attention.